Hello class. So today we're going to be discussing Newton's method. Now Newton's method is a process devised by Isaac Newton in the 1600s for approximating the root values of functions. What are the zeros of our function? And Isaac would often use this method to approximate the zeros of complicated functions, or functions that cross the x-axis in many different places, like the one we've drawn here. Now this function crosses the x-axis in 5 separate spots. But how would we go about determining these values? Well, let's take a look. If we were working with a quadratic function, we could use the quadratic formula to determine the value of these zeros. If our function was a cubic, there's a cubic formula for determining the values of these zeros. And there's even a formula for quartic functions, or functions that cross the x-axis in 4 places. Now, if your function has 5 or more roots, there's no formula for determining the values of these roots. This is a problem in mathematics known as the unsolvability of the quintic. So we have to arrive at these values using other means. We could get there algebraically, but to find the zeros of a higher order equation using algebra can be rather complicated. Newton decided to use derivatives. He then wrote an algorithm, which when repeated, will give us closer and closer approximations. Here's how it works. So let's say we want to find the value of this point, where the function crosses the x-axis at this point. What Newton would do is, the first thing is he would go ahead and take a guess. He would try and find somewhere that he thinks is close to this point, and he would go ahead and plug that value into the function. He's going to evaluate his function at this guess. And what that gives him is the height of his function evaluated at his guess. Now he's trying to determine some information surrounding this point. So what he's going to do, he knows his guess is close, is he's going to go ahead and he's going to take the derivative of his function, and then he's going to evaluate that derivative at his guess. And that's going to give him the slope of the tangent line that runs through that point, this point on the function. Now, if you look at this tangent line, follow it down to the x-axis, we can see that it crosses the x-axis at a point that is much closer to our point of interest than our initial x1. Let's call this value x2. We know the value of x1 because this is the value that we've been plugging into our equation. And we know the slope of our function at this point. Let's call that f prime x sub 1. You see the little prime mark? Okay, so this is essential information, because at this point we want to determine what the value of this is, and this is going to be the next little bit of information that we need to determine. What is this distance here? What is this change in x? Because we can look at our guess. If we can subtract this value from our initial guess will arrive at x sub 2. Alright, so what is this change in x? Let's look at the definition of slope to come up with that value. We know that slope is equal to rise over run. Well, let's look at our graph. At this point, rise is going to be equal to our height, f of x sub 1, our function evaluated at our guess. What's the run? The run is going to be this change in x. If we do some cross multiplication, we can bring the slope down to the denominator and bring the change in x across. Now, what is the slope at our guess? Well, we know that to be the derivative of our function evaluated at our guess. So this is one way to determine this change in x. So if we want to find x sub 2, we can basically write that as x sub 1 minus this change in x will give us x sub 2. Now, Newton's formula is very similar to this. He writes x sub n plus 1. This n represents our guess. You know, this is an iterative optimization algorithm. Iterative as in you can do this process over and over and over again, and this tangent line is going to get ever and ever and ever closer to this point until you're able to very, very accurately approximate this value exactly, or as close to exact as you'd ever want to get. That's what this n plus 1 is. This just represents an iteration through the process. So your first guess would be, your first n would be 1, n plus 1. You're going to get a 2 there the next time. So this is your initial guess minus your function evaluated at your guess over the derivative of your function evaluated at your guess. And this, my friends, is Newton's method. Okay guys, so we've gotten a look at how Newton's method works. Now let's actually put it to use evaluating the roots of a function. So the function we're going to be working with today is x times the natural log of x plus 1 minus 1. So we know from our demonstration that to use Newton's method, we're really going to need 3 pieces of information. We're going to need this first initial formula, this initial equation, excuse me. We're going to need the derivative of this equation, and then we're going to need a guess. This is our starting point. This is the guess that we think is, you know, as close as we're going to get to what we think that root is. So let's start out with finding our derivative. You know, we're going to be doing the product rule here. We've got a constant at the end that's going to end up canceling out, so this won't be included in our derivative, but it's going to look something like this. It's going to look like the first times the derivative of the second. Now we're using quick rules here, and that's something that's been covered in class already. So if you're wondering what I've got going on here, just look up product rule, quick rules for derivatives, and you'll see where I'm going with this. Let's see, plus the second ln x plus 1 times the derivative of the first. So if we work this out, we see that our derivative is x over x plus 1 plus the natural log of x plus 1. This is what we're looking for. Now, as far as our guess, what would be a good first guess? Let's return to our original function. So, I know by looking at this, it's got a natural log. We're going to have a domain restriction. You can't take the natural log of anything that's not positive. So anything within this parentheses, if it's 0 or negative, it's going to give us an undefined, it's going to give us an error message when we try and graph it. So I know -1 plus 1, that's equal to 0. So it can't be anything -1 or less. So right there, that's our domain. It's got to be greater than -1. What if we evaluate this function at 0? What's that going to give us? Plug 0 in for this x, 0 plus 1. This looks like we're going to end up coming up with -1. -1. Because 0, whatever is in this value, it's still getting multiplied by 0. So -1 is our value if we plug in 0. I'm gonna guess one closer. You know, let's see what our function evaluates out to if we plug in 1 for our x value. ln of 1 plus 1 minus 1. -0.30685, and so on and so forth. So we can see that this value is actually a lot closer to 0 than 1 even is if we were to plug in 0. So this is actually a great starting guess. This gets us really close from the very get-go. So here's our 3 pieces of information. Let's go ahead and just write out Newton's method, just so we have something to reference. X sub n plus 1 is equal to our guess minus our change in x, which is written as our function evaluated at our guess over the derivative of our function evaluated at our guess. And at this point, I like to usually set up a little chart. So let's let this first column equal our initial guess. This column can be our f of x sub n. This can be our derivative at x sub n. And this will be the closer approximation that the formula gives us. This is the number we're looking for. So our initial guess is 1. Let me just draw some columns here so we're not letting our numbers all bleed together. Don't you hate when that happens? Anyways, so we already plugged 1 into our initial function, and we got -0.306852819. All right, let's go ahead and plug 1 into our derivative function. So I'm going to set up a fraction bar. That's going to be 1 over 1 plus 1 is 2, plus the natural log of 1 plus 1 is 2. What do we get? 1.193147,181. Now we've got our guess, we have our f of x sub n, and we've got our derivative at x sub n. We've got all the information we need to come up with this closer approximation. So let's go ahead and plug that into our calculator. So this would be 1 minus, set up another fraction bar. Let's see, negative 0.306852819 over 1.193147,181. 1.25717. This is our closer approximation. 1.257179352. So this basically tells me that my 0 is actually further along the x-axis. It's a little bit more than 1, because I have a feeling this number is going to get just a little bit smaller. So we know it's definitely between 1 and 2. What I'm going to do is I'm going to go ahead and fast forward the video here and run through this iteration a few times, and we're going to try and get this number to be exactly the same up to let's say 6 or 7 decimal places. At that point we can basically stop, because we know, okay, if we continue further through the process, we're just going to keep getting closer and closer approximations. But I'll be satisfied with 6 or 7 decimal places. Okay, cool. So as we can see, we went, let's see, 1, 2, 3, 4 passes through. That gave us accuracy out to, that's 1, 2, 3, 4, 5, 6, all the way out to 8 decimal places, even more than we were asking for in just 4 passes through the formula. One thing I forgot to mention before I sped up the video there is we want to remember this is the value, this is our x sub n plus 1, so through each iteration we're going to take this value and use that as our x sub n value. So you get this value, you plug it in, run through the process, get a new value, plug it in, run through the process, and that's how we're going to get to this close approximation. Now we know this right here is one of our zeros. Let's go ahead and run through this process and try and find our second 0. Alrighty guys, so now that we went through this process once, we've got our first 0. We need a decent guess to go ahead and start with so that we can find our second 0. Now, I chose -1/2 as the number for my second guess. How did I arrive at this number? Let's just go ahead and talk about Newton's method for a second. So this is not a foolproof way of finding zeros. If you have an initial guess that is not close to the root that you're searching for, if you plug it into this method here, you might see that it's trending towards an answer that you've either already found, or if it's a function that has multiple zeros, it crosses the x-axis multiple times, it might trend towards a 0 that you're not interested in. So you want to know some basic information about what your graph looks like so that you can pick a first initial guess that is going to get you towards that root. So what I did is I took my initial function and I started plugging some values into it and seeing what they were. The higher x values that I plugged into the function, I was noticing that this y value was increasing upwards, and so I saw that it was always increasing upwards towards infinity. Now we already know that there's a 0 at 1.23, so it crosses down, the values become negative there. If we plug 0 in, right there we know it's equal to -1, but anything less than that, getting closer to our domain restriction, the values started to trend upwards again. And if we plug values in that were very close to our -1 domain restriction, they actually started to switch over and became positive again. There was a sign change. It changed from negative here to positive the closer that we got to this -1 on the x-axis. That sign change indicates a passing over of the x-axis. So we know that somewhere between -1 and 0, there is going to be a root. That's enough information to get us close enough to make this method work. So I'm going to go ahead and run through Newton's method the same way we did when we were looking for our last 0, and let's see if we can determine what this second 0 is going to be. Alright guys, so it looks like we've landed at some repeating decimal places here. So we've got this 0 accurate to 1, 2, 3, 4, 5, 6, 7 decimal places. We're comfortable with that. So we know like I mentioned before, that this graph definitely crosses the x-axis around -0.74. So actually pretty close to that domain restriction. One thing running through a few iterations of this method, I noticed, we were kind of trending towards this 7.4 value, and then it seemed to skip right here, like it looks like it jumps out of place, and we have a sign change, but then it gets back on track. And I don't know if that was just an error in how I was inputting this into my calculator, but I have noticed that on some other occasions you'll see it trending in one direction and then it'll kind of like skip over and like correct itself. So that would be an interesting thing to look into as well, if that's just the nature of this method. But yeah, here is our second 0. Now, we've got our first, we've got our second. Let's go ahead and see how we did, guys. Let's plug our initial function into our graphing calculator. I've got it set up right here. Let's see what these values are, or what these zeros are. $1.2399779. All right, so we see our first 0 checks out. Newton's method worked for that one. Let's go ahead and look for our second 0. -0.7407536. So yeah, we're accurate. It works. Alrighty class, so for our second demonstration of Newton's method, we're going to be approximating the square root of 2, and then I'm going to show you how to do that on our TI-84 calculators. So let's write down square root 2. All right, we want to find, so we'll set our variable equal to root 2. But see, if we were to graph this right here, we would end up with a vertical line at this root 2 value, and the slope would be undefined. It's not really giving us any more information than we already have. We want to be able to convert this into a decimal, as far out as we need it to go, depending on how accurate we want to get that. So what I would do is I would solve for x, and I would set that equal to 0. So here we have x squared equals 2. If we subtract 2 from both sides, we'll have x squared minus 2 is equal to 0. And this function here will serve as our f of x. F of x equals x squared minus 2. Now we know from our previous demonstration that we need 3 values. We need a guess, we need this f of x evaluated at a guess, and we need the derivative of this function evaluated at a guess. So let's find, before we determine a guess, let's find the derivative of this function. Using our quick rules, we know we can bring down the exponent. 2 minus 1 is just 1, so there's an invisible 1 right there. And then the derivative of a constant is just going to cancel out. So this right here is going to be the derivative, and this right here is our initial function. And then we'll take a guess. Okay, so what would I do as far as guessing what the square root of 2 is? Okay, well, I would probably do something like this. I would probably say 1 times 1. Let's see, can you see that? 1 times 1 is equal to 1. All right, but what is 2 times 2 equal? That's equal to 4. I'd get a little closer. 1 times 1. 1.5 times 1.5. Yep. 2.25. 1.4 times 1.4. What's that equal? We're getting closer at this point. 1.96. So that's pretty close. I'm going to go with 1.4 as my guess. So we can say my x sub n, we're going to plug that in as 1.4. Now, let me show you a method for figuring out a close approximation to what root 2 is without having to go through setting up the chart like we did last time and doing every iteration through the process each time. There's a way that we can use our calculators to basically do that for us. So here's how that works. First, what you want to do is you want to go to your y equals, I've already have that other value in there, but for y1 you want to plug in the original function. So we've got x squared minus 2. This is our original function. For y2 we want to plug in our derivative function, 2x. Then we can go back to, I call this screen like the workbench of our calculator. At this point, we can plug in our guess. If we press enter, that's going to save this value into our answers key. So you see, if we go here, second answer, and press enter, this value has been saved under the answer function. Now we can actually set up a formula, that we can just like tap through enter, and it'll repeat the formula over and over again without us having to plug values in each time. So we'll get our answer going, minus, I'm going to set up a fraction bar, And then if we go to variables, y variables, function, I can actually pull the function that I have typed into my y1 value, and I can evaluate that at any number I want. Well, nope. If we plug an actual value into there, then we won't be able to iterate. So we hit second answer. Our derivative function is going to go under the bottom. y2. We want to evaluate that at our answer, which is 1.4. And this, I'm going to press enter, and this will give us a value that is closer to root 2 than our initial guess. Let's try it. 1.41428. Let's do it another iteration through. Okay, see, it looks like it's getting closer. All right, now we're getting repeat decimals. So let's actually plug in the root 2. Root 2 is 1.41213562. So yeah, this is accurate out to whatever this is, 8 or 9 decimal places. How soon through the process were we able to get that close? Okay, so our first guess looks like it got us 1, 2, 3, 4, 5, maybe 6 decimal places. There was some discrepancy here. And after the third iteration through the process, we were able to get accuracy to 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. 9 decimal places of accuracy in just 3 iterations through.
Greetings, Earthlings. Alrighty, so here we are in Excel. This is Microsoft Excel. I'm going to demonstrate how to run through Newton's method using this program. So right here, this is actually our first function that we evaluated. We found the roots of this x times natural log x plus 1 minus 1. We did this in our first demonstration of Newton's method. This is our derivative of this function, and then this is just mostly just for my reference. You know, this section here just says x sub n plus 1 is equal to, it gives Newton's method right here, and then this is a big line of text that is mostly for my reference so I know what values I'm plugging in. These 3 lines aren't acting on the program. All the work of the program is being done in these cells down here, which I'll demonstrate how to design your own cells and run the program later on in the page. I just wanted to mostly just show you guys and Mr. Baxter that more complicated function we were working with at the beginning, we are still able to find our roots to a high level of accuracy. You see all those decimal places are all identical towards the end there, using this program the same way as if we were to use our TI-84 calculators. So I'm going to go ahead and show you how to basically do the same process, but with trying to approximate the square root of 2. So I'm going to go ahead and just write my functions here, and like I said, these aren't actually like acting on anything right this moment, and they won't. I just like to have them in front of me so I know what I'm working with. Okay, so now that we have our information written out, we can start running through the program. So I'm going to designate this cell as our number of guesses. and I wanted to say 1, let's do 10 iterations through. So I'm going to put a 1 right here. And then how am I going to get the rest of these blocks to say 1, 2, 3, 4, 5? I don't want them to just all say 1. So what we do here in Excel is we click on the cell. If we start typing with an equal sign, that tells the program that it's about to, it's about to run an equation basically. So I'm going to go ahead and type that equal sign. By clicking on this cell right here, I'm referencing that cell. This is cell C24. So the value that's in this cell just got inserted into this other cell. And then I'm just going to do a +1. And if I grab this little corner right here and drag down, every value that I have in this cell is going to get added to the next, and that value is going to get added to the next, added to the next. It's always going to be +1, greater than the value before. Okay, so we have 1, 2, 3, 4, 5. We got it all the way up to 10. Oop. I'm canceling that. Now this guy over here, this is going to be our x sub n value. I recall from the first demonstration, my guess was 1.4. So this is the value. Anywhere you see, okay, so anywhere past this equal sign, this is Newton's method right here. X sub n, this is 1.4 minus 1.4 squared minus 2 over 2 times 1.4. This is the equation that we're going to use to approximate these zeros. Anyways, we'll do the same thing in this column. You go ahead and click on the cell. And see, the reason there's so many decimal places, I've got this program set up to round to like 20 decimal places. Just I want to see how accurate this thing can get. So we start out with an equal sign. And now anywhere we see an x sub n, I see an x sub n right there at the start, a minus 3 parentheses, another x sub n. We're doing, this is the symbol for exponent. Oop, I don't want to forget to close the parentheses. So back to the symbol for exponent, minus 2, close parentheses. This is the symbol for division, 2 asterisk is multiplication. We're going to reference this cell again, and then close the whole thing with parentheses. I really like how they color code the parentheses in this program, because you can always see, you're like, all right, this purple parentheses is closing the start of this D24, and the red one is this little cell right here. The black one, wow, that covers the whole equation more or less. Now if we press enter, wow, that value is really rather large. Or not rather large, it just goes out to quite a few decimal places. You got to click on your initial value that has the equation. Go to the corner, you're going to see a black plus sign, and just drag it down. And this is what iterates your equation. But as you see, starts to get, see right here, there's a change, and it seems kind of odd. It's like back and forth between 3.1 and 3.09 here out at like 11 or 12 decimal places. I wonder if that's just a limitation of this program in particular. But that's interesting how we can only really get the accuracy out to like 10 or 12 decimal places. I'm almost willing to bet that's the accuracy of just Excel, this program in general. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's accurate. They're identical out to 12 decimal places. So that's pretty high level of accuracy, I would say. Anyways, that's how you run through Newton's method using Excel. On to the next example.
Okay, so today we're going to be looking at a very basic, this is just like a skeleton of a program to run Newton's method. Very straightforward. It's gonna we plug in a function, we plug in the derivative of that function, we give it a guess, and it's going to approximate our zeros. So just very basic. This isn't we're not you know using AI or deep learning neural networks here. We're just plugging a function in and approximating a zero. But this is where it starts. So I want to give you a basic rundown of what's happening when we type up something like this. So in our first line here, we're just going to go ahead and assign our guess. So my guess is negative 1/2, negative 0.5. So this is a numerical value. I'm going to use this equal sign operator to assign that to this variable x. So later on in the code, when we refer to that x into whatever this function is defined as, is going to be inserted this numerical value. So that's what the function will run. This is just for my just for me to reference, because anytime you type a pound symbol, anything after that on this line is not going to be ran by the code. So this is just pound, type anything after that. It's a good way to give yourself little reminders, little notes in the code, so you don't get lost. I'm assigning a numerical value to the string value iteration, which I call on later here. Okay, for this program, we're going to need to import, there's these like function libraries, math. If you type import math, that allows us to access the math library, which lets us do things like take the natural log of numbers and variables. So that's what I'm doing here. Here we go. We're just defining our first function, and in this code we're working with the same function that we've used in previous demonstrations. This is x times natural log x plus 1 minus 1. So that's what we're doing in this block of code. When we return this f of x value, that saves this information into this variable f of x. So that's what Python is saving into f of x. We'll have a number in here. It gets evaluated. Here, and then it gets assigned to this guy right here. Well, we're doing the same thing with this, but this is our derivative function. If you'll recall, x over x plus 1 plus the natural log of x plus 1. So here's where we actually start to go down, and iterate through the process. For item in range, we're going to start with our first guess. This value here is 15, which we've assigned up here. And then this is our step. We want to go up in increments of 1. It wouldn't really make sense to go up in anything other than 1. I don't even know if the program would work if you went up in steps of 2 or 3, because then you're skipping over x sub n values. That'd be something interesting to fool with. But you see, we're calling on our functions. We are, we're printing out the information that our functions are providing for us. And then we're reassigning our x value, so that when we iterate through this process again, we're not just using the same guess over and over and over, because we would just be getting the same value over and over and over. We want to get consecutively closer x values. So at the end here, we reassign our x value by labeling it as x minus the change in x, Well, that's basically just the bare bones of how this program works. Now, if we press F5, we should be able to get this thing to run. Let's see. Okay, yeah. Here we go. So I've got it set up so it shows our x-intercept here. This is our guess, basically. The x-intercept, and then there's our y value at that point. But you see how through 15 iterations it's getting closer and closer to what the real x-intercept is. And with this e-16, this is basically a y value of 0. Not quite, but very, very close. And if you'll refer back to our previous demonstrations working with this function, you'll see this x value here checks out. Now, if we manipulate this guess, let's change it to 1, like our other guess was. Yup. Okay. And we'll see 1.2399778. Yep. Python gets it accurate to much more decimal places than even our calculator was able to find. So this is interesting. Yeah, this definitely works. So guys, if you have if you got a function and you want to find the x value, the decimal value of your x-intercept, and you're finding, okay, heck, I want to get accurate out to, what is that? That's probably 12, 13, or 14 decimal places. Our calculators only give us out to, like, say here, or maybe here. So if you want to get accurate out, like, to almost twice as many decimal places, maybe try plugging it into Python.